Welcome back to the next episode of, okay. So here we go. We have a function. We need to find the derivative of it first. What are we going to need to do to find the derivative of this? Quotient rule. Yay. Yay. We have no trig, but we have quotient rule. So denominator. Derivative of the numerator. Numerator. Derivative of the denominator. Over denominator squared. Okay? F prime of x is equal to, I'm going to multiply by 2x here. I get 2x cubed plus 6x minus, this looks like 2x cubed, yeah? So, with a little bit of simplifying here, we see that our first derivative is 6x over x squared plus 3 squared. Now, in the world of AP Calculus on exams, you are going to come across quite a few rational functions like we have here, fractions, where we have to think carefully about what's happening with the derivative. The derivative is going to be undefined if the denominator is 0. The denominator cannot be 0, right? So this is where like the critical thinking kicks in, and there's not just like some hard and fast rule. Like I'm thinking about this here, okay? I know that f prime is undefined. F prime is undefined if the denominator is 0. But when I look at this, I have x squared plus 3 would have to be 0. I'm squaring it, but x squared plus 3 would have to be 0. Now, when I square x, it can't be a negative number. I can't get negative 3. We're dealing with imaginary numbers. That's not a thing in calc. Denominator, never going to be 0. When is the numerator going to be 0? When x is 0. 0, okay. So f prime equals 0 when the numerator is 0. Okay, that happens at x equals 0. So from some quick analysis here, I find that there is only one critical number. The only critical number that we have here is 0. Okay? Now, I'm dealing with all numbers in the world again. I'm talking about f prime. There's only one critical number. Only one critical number. Okay? I also know that my denominator is always going to be positive. Right? I can't square something and get a negative number. So my denominator is always positive. When I put negative numbers into the numerator, my numerator is negative. When I put positive numbers into my numerator is positive. My f prime is positive. Okay? So now, this tells me that my function, my f of x is increasing when x is greater than 0. F of x is decreasing when x is less than 0. Much easier than the last problem, right? What is happening at 0? We have a relative what at 0? Please say it. Relative at 0. Min. Going from negative, it's going down. My f of x is going down. It hits that point, and then it's going up. Minimum. So we have a relative min. We have a relative min at x equals 0. Okay? No relative max. There's no relative max at all. Okay? So look, we're making like light work of this, right? Now we're going second derivative. We're already on to the concavity part. So I've got my first derivative here is 6x over x squared plus 3 squared. Okay? Now I got to try and get the second derivative out of that. Okay? So my second derivative, I'm going to take my denominator times the derivative of the numerator minus the numerator, derivative of the denominator, 2 times x squared plus 3 to the first times 2x, because I got to do chain rule. Okay? So to get that, I'm doing chain rule to get the derivative. That's what it says. Okay? All of that divided by x squared plus 3 to the fourth, because I'm squaring that. Now again, it's easy to look at this and go, oh my, that's like terrible. That is absolutely terrible. But we do know that the denominator is always positive still, right? Denominator is always positive. Always positive, never going to be 0. Okay? That's helpful. So really what I'm working with is my numerator. In my numerator, I've got 6 times x squared plus 3 squared. This is 2x times 2 times 2 times 6. So like negative 24 x squared plus 3 over x squared plus 3 to the fourth. Okay? Now, I got to try to figure out where f double prime is 0 so that I can make my number line and carry on with my business, right? So 6 times x squared plus 3 squared minus 24x squared plus 3. I want to know when that equals 0. And this is where, maybe the tears start to flow. Like, I got an equation. I know how to solve equations. I did that in my algebra classes, but I was never told I'm going to have to solve equations like this. Okay, and I've never seen anything like this. But I do know that like something that I've done a lot when I'm simplifying is I've pulled out a common factor. Is there a common factor in those two terms? X squared plus 3. So I'm going to do that. I'm going to pull out a common factor and see if that might help my cause. So I have a common factor. And I could pull out a 6 out of that too, right? So I have a common factor of 6 x squared plus 3. Okay? That's my common factor. And then what's left behind is x squared plus 3. There's one extra factor there. Minus, there's 4x squared left here. Okay? And I'm trying to figure out where that's equal to 0. Again, did you just see what I did? I pulled out a common factor right here. Okay? Then what's in parentheses here is my Thanksgiving leftovers. You got a little turkey, you got a little gravy, some stuffing. Okay? It's all there. Now, why, Mr. Tubby? Why do you do this? Please teach me your ways. Okay, look, if I have something that equals 0, and I can get it as a bunch of factors, then I'm in great shape because I can say each one of those factors, I'm going to look for when that equals 0. Okay? Does 6 equal 0? Nope. Is x squared plus 3 ever going to be 0? No. Dead end, right? Like these are dead ends. Not going to happen. Here, I've got negative 3x squared. I'm adding the x squared and then minus 4x squared. Plus 3 equals 0. So I get negative 3x squared equals negative 3. Divide by negative 3. So I get 2 locations plus or minus 1. I get 2 locations where my second derivative is 0. These are possible transition locations for the second derivative where it could be going plus to minus, minus to plus. Okay? So now, we got this here. I'm going to draw myself a number line. I've got negative 1, positive 1. I'm going to test my second derivative. I'm going to test it full on knowing that this is my numerator right here. This is my numerator, and I know my denominator is always positive. My denominator is always positive of my second derivative. Okay? If I put 0 in to the numerator here, if I put 0 in, I get 6 times 3 times 0, 3. 6, 3, 3. When I put 0 into the numerator, I get a positive number out. When I put 0 into the denominator, it's always positive. This interval is a positive interval. Okay? Think about what happens here when I put in a number like 10. Okay? So I've got negative 3x squared over here. Putting 10 into that's going to make that factor negative. This is a positive factor. Positive, positive, negative. When I put in a number like 10, 100, 1,000, this third factor is going to be negative. The other two are positive. Negative divided by positive, I've got a negative. Okay? When I put in something really negative and I square it, it's going to, I got negative 3x squared, right? I put in negative 10, I square it, I get 100 times negative 3, negative. Same kind of actions going on. I got negative over positive. I have to somehow convince myself that when I put in a number in this interval into the second derivative, that I end up with a negative value. Okay? This is telling me my graph is concave up from negative 1 to 1. It's telling me my graph is concave down when x is less than negative 1 and when x is greater than 1. And it's also telling me that I have inflection points at 1 and negative 1. Take a picture. Okay. Again, let's check this out. Original function, f of x is x squared over x squared plus 3. This is what our graph looks like. Am I buying that there is a minimum at 0? Absolutely. Definitely looks like a minimum. Am I buying that there is a change in concavity at negative 1? I am, because watch what happens at negative 1. Like if I draw a line here at negative 1, this graph, it doesn't look very curvy, but you can tell it's concave down. Yeah? And then for this little section in here, it's concave up. And then when I hit x equals 1, it goes back to being concave down again. Okay, that's what it looks like graphically. Okay, any questions about that problem? 13.